Well, we've already done that one. Suppose we better do that one next. Time for pH probes, folks. Hi folks. So yeah, today we're going to be doing EC measurement, and I've got my EC pen that I bought, I don't know, 6 months, 12 months. So this week I've been reading up on pH probes and working out how they work and what makes them tick. Let's start off with a look at a couple of EC probes, and I'll try and explain what's going on with them. Okay, so here is my pH probe, which at the moment, interestingly, is telling me a pH of 2.3, which is probably wrong. Let's stick it in my tap water and see what it works itself out to. Tap water normally weighs in somewhere about 7.8. Once this thing's had a chance to warm up. And actually, just for fun, while that's taking its measurement, we'll get one of these strips of litmus paper, which I strongly recommend everyone has a set of litmus paper kicking around. They last forever, and it's just so, well actually, yeah, these ones were 2008, these have been around since, but they last forever and they don't go wrong. And if you're ever in doubt of your, oh look, we're up to 7.8 as predicted. If you're ever in doubt of your pH meter's calibration, it's very, very quick and easy to dip a strip of paper in and see where we weigh up on the scale of things. And well, I think we're 7.8, and we're certainly looking somewhere around 7.5, 8.0 on the readings there. 7.9 now our pH probe says. So how does this all work then? Well, if we have a look at the end of our pH probe, you can see we've got a little glass ball there, and something that looks kind of like the end of a felt tip pen there. They're actually rubbing my fingernail on it. It's a lot harder than a felt tip pen. It feels like some kind of ceramic style thing. Let's have a look at another pH probe as well, because I bought another one of these for trying to do some automation. And let's have a look what we've got in here. This one was dirt cheap. This cost £5.50 including delivery off eBay, and comes with the end of the probe dipped in this little pot of stuff. And if we have a look at the end of this probe, you can see we've got a glass ball there, the same. And I don't know if you can see, let me just get a little pointy thing. If you can see, down the side there, we've got another little stick. And it's basically the same as in that little pH pen. It's another bit of kind of stuff that looks like felt tip pen, but it's much harder and feels like ceramic. So we've got a couple of them, one either side, and we've got our glass ball in the middle. And down this probe, I don't know if you can probably see on the camera because it's generally quite big, you can see there's one wire here going down the outside, and there's another wire there running down the inside. So I've done a lot of googling on this to try and work out exactly what's going on. Seriously, I spent like 2 days reading up on pH probes until I found all the information I wanted. So I'll give you a rundown on my understanding of how they work. Now, although these two probes look very, very different, they're actually both exactly the same, or pretty much exactly the same. So what we've got going on, I'll explain this tube first. This is called a combined probe, apparently. So let me see if I can explain what's going on with this. Hopefully I'll have this the right way up. There we are, it's about square in the frame. So how these electrodes are made, well, first of all, they start off with a glass tube. Nothing special, just absolutely normal glass. Onto the end of that glass tube they add a different kind of glass, special magical glass, and they blow a little bubble. So you end up with a little bulb at the end. And this bubble is very, very thin. The thinner they make this glass bubble, the quicker the probe reacts to measurement changes and kind of the more accurate the probe is, but obviously the less mechanically robust it is. So it's always a trade-off between the thickness of this glass bubble and the accuracy and speed that the probe works out. Typically this glass is somewhere from 0.2 to 0.5 millimeters thick. So very, very thin. When I say this is magical glass, this is glass that's actually been doped with, generally I think they use lithium ions, which gives the glass itself a bit of a negative charge. And this is what's called an ion selective layer. And what this means is when this piece of glass is put into a solution, any hydrogen ions which are positively charged, the H+ ions, are attracted to the lithium ions, and these hydrogen ions kind of bind to the glass on the outside and they form a very, very thin layer that's something like 2 nanometers thick. Very, very thin layer where these positively charged hydrogen ions are finding the negatively charged lithium ions, and they're just building a little layer on the outside of that glass up. Now inside the probe they put a silver wire, and the silver wire goes down, and inside this probe they fill this bit up with basically a buffer solution, something like potassium chloride, so it's KCl. And this wire down the middle is silver so that it doesn't react with anything. So we've got KCl liquid inside this electrode, and we've got positively charged hydrogen ions attracted there. Now at the same time that's happening on the outside of the glass, we've got positively charged hydrogen ions attracting on the inside of the glass as well. So what you end up with is a bunch of H+ around the outside and some more H+ on the inside of this glass. And we get a layer that builds up on both sides of the glass. Now if everything's equal, if the pH, now actually I should probably say pH is actually a measurement of the hydrogen ions free in a solution, and this is what determines the acidity of it. The more acid something is, the more hydrogen ions it has free roaming in the liquid. The more alkali it is, the fewer it has. I hope I've got that the right way around. Let me just check there. Yes, I was right. So yes, so a low pH means we have lots of hydrogen ions, and a high pH means we have very few hydrogen ions. Now our reference potassium chloride solution will have a pH of 7.0. Now if the solution we've dipped our probe into also has a pH of 7.0, then what you get is you get the same number of hydrogen ions attracted to the outside of the glass layer as are on the inside of the glass layer. So there's no actual difference between the two, and this would give us no voltage, no potential difference, no voltage on our silver wire here. If you get the situation where this pH is, this solution you've dipped everything into is more acid, so something like pH of 4, then you get more hydrogen ions on the outside, and those will oppose the hydrogen ions on the inside, and you get these little positive charges in this liquid, and you get a voltage developed on here, on this silver wire. And this is basically how it works, but of course we can't extract any current on that because we haven't got a circuit, we haven't got a way for the electricity to flow through. So they actually add in a second electrode, this one's called the measurement electrode, and they add in a second electrode which is called the reference electrode, and this must sit down in the same liquid. Now these can be two physically separate electrodes, or they can be combined into one unit like this, and I'll show you how they do that in a minute. This reference electrode is also filled up with potassium chloride, the same solution. So the pH in this electrode is actually the same as the pH in that electrode. This one also has a silver wire going down inside it. So these come up to, these two wires come up to the BNC plug on the end of our probe, connects direct to those two. So we've nearly got an electrical circuit there, but obviously this is just a straight glass tube and glass doesn't conduct electricity. So we need some way here for this wire to effectively be in electrical contact with this solution. But we don't want the electrochemistry happening. We don't want to just stick a piece of wire straight in this solution. So they use what's called a porous junction for this, or a liquid junction. And these are the little bit that looked like the end of a felt tip pen here. And what this actually is, this is a porous tube. They can make these out of a variety of different things. The ones in both of my electrodes are made out of some form of ceramic, and basically this ceramic will soak up the liquid inside the probe here, inside our reference probe, and also soak up the liquid from our solution. And inside this probe, inside this porous junction, the two liquids meet in a liquid-liquid interface. And that gives us almost an electrical circuit. Now, I spent a long time trying to find out how this was happening, because I could see as charge built up on the outside of our measurement electrode that it would create a potential difference across this layer, and this wire could detect that, and I can understand that we need a current path, but we haven't quite got a current path here. We haven't got anywhere current can actually flow because we've still got a layer of glass here. So I spoke to a friend of mine who's a scientist who does all this for a living, and he explained to me that because they've doped this glass ball with lithium, this is actually ever so slightly conductive, in the range of 500 megaohms, some ridiculous resistance, more than a multimeter can measure. But this is very high resistance layer, and basically these charges on the outside can make their way through to the inside, and then we get a voltage across this wire and we can actually measure this. So this will give us an output voltage, and depending on the strength of the solutions, if we're down at a pH of 1, or sorry, up at a pH of 1, which is very acidic, then our probe will give us out round about 410 millivolts. And if our pH is right up at the other scale, we've got a very strong base, very alkali, we get a charge of round about minus 410 millivolts. So what this pH probe is basically, this is like the world's most rubbish battery. You can't pull any current out of it because it's got this layer that's almost entirely an insulator, just past nanoamps of current. Even if you strung 100 of these pH probes together, you'd have a hard time lighting an LED off them. The current is minuscule in this. The next thing I thought was, okay, so if we've got hydrogen ions from this solution outside slowly making their way through this glass to the inside, aren't we going to be changing the pH of this potassium chloride solution in here? As we start adding more hydrogen ions into here, this is actually changing the chemical balance of this. And yes, that's exactly what happens. And also the same is going on with this porous junction in our reference electrode. This is exactly the same thing happening. We've got whatever liquid we're measuring, and basically this is, you know, it's like damp cardboard effectively. The liquid doesn't really flow through it, but you're going to get some contamination from whatever you're measuring making its way into this reference electrode. So I was kind of curious as to how this worked then, because surely these electrodes, if we're taking up this solution in this one and we're taking up the hydrogen ions in this one, surely these electrodes must wear out then. And indeed, yes they do. The instructions for my pH pen says, care and maintenance, this pH tester can accurately measure 365 tests for 1 year based on 1 test per day if the sensor is maintained. At this time the sensor will degrade, but regular cleaning and calibration of the unit will prolong its life past the expected amount of tests. So this glass here is the very thin layer of lithium doped glass that I was talking about, and this is our liquid interface, our liquid junction, porous junction. So inside this probe we've got exactly what I've shown on here. We've got our two different electrodes. These wires come off to a circuit inside where they amplify this signal, read it with a microprocessor and display it on the screen. Now inside this one what we've actually got is the same two electrodes I've drawn here, but they're done as a tube within a tube. So actually this reference electrode is just living around the outside of that one, and our porous junction comes down there. And in fact in this particular one we've got two porous junctions, and I'll just show you them again. So we've got one porous junction just there, and on the opposite side we've got another one there. Now this pH probe in particular has got a little fill hole just there so that you can replace the potassium chloride solution in the reference electrode, because that will take up contaminants. So that's the kind of care and maintenance for this probe. This is how you extend its life. This one, however, there's no way of refilling it, there's no way of servicing it, which is why this one is dead after a year, provided you take proper care of it. I will admit I've never taken proper care of this probe at all, ever. They say always store it with the lid on, but the lid was a pain to get on and I couldn't get it off with one hand and things like that, so I kind of just gave up storing the lid on it. Of course, now I've looked into all of this, I realise that was a really bad thing to do, because obviously my reference electrode will be evaporating through that porous junction, and this little glass ball could be getting all manner of rubbish building up on it, and I've never stored it right. So, well, from now on I'm going to store it with the cap on. Right, so I've already told you that this pH probe is like the world's most rubbish battery. You can't really pull any power at all from this, and we need to amplify this little tiny signal into something that we can pull a bit of current out of, and most importantly that we can plug into a microprocessor. So what I'm going to do, or what I have done this week, is I've built a little circuit for running this pH probe. My circuit's very, very simple. What I've done is I've taken an op-amp, and I'm not going to explain what op-amps are. There's millions of videos, well, thousands of videos on YouTube with people explaining it, and they probably understand it better than I do. But this is basically a very, very simple amplifier, and you have two inputs, an inverting input and a non-inverting input as they're called, and the job of this amplifier is it's trying to make that one equal to that one. If that one has a higher voltage than that one, then this output goes high. If it has a lower voltage, then the output goes low, and that's all I'm going to say about it. But if we hook the output voltage round like that, negative feedback this is called, and we hook our pH probe across here. So here is our probe. Don't know how to draw that, let's just draw it as something funny like that. That's our pH probe. Then whatever voltage we put on here, so let's say we got 210 millivolts on there, we're going to get the same voltage on there, because this is going to do whatever it takes to make those two equal. What it takes to make those two equal is this output voltage being lifted up to 210 millivolts. So this is basically acting as a buffer stage. I'm using these operational amplifiers, in particular it's the same one that I used on my EC probe, because they have a ridiculously high input impedance. Basically no current flows through the inputs. So this is what's called a unity gain buffer. Multiply by 1, and that's all it does. Now the next part I need is something to change that tiny little voltage level into something I can use with a microprocessor input, which really I'm looking for an output of kind of 0 to 5 volts to represent pH of 1 to 14. So I need to take this tiny signal and I need to multiply it up and shift the voltage level, and we do this with another op-amp. We have our 2 pins once again. So these two resistors I've just drawn in here set the amplification, how much this will multiply the signal, and with 10 on the input and 100 on the feedback, we're actually making this into a times 10 multiplier. So if we put 210 millivolts in there, we get 2.1 volts out of there, and on this pin we're hooking this up to a resistor network, and this resistor network sits between positive and negative. Oh, let's draw another one in. I've drawn a fuse now. This resistor network sits between positive and negative, and by changing how much positive or negative this pin is, we're shifting this relative to 0. So if we shift this pin up, our voltage shifts up. If we shift that pin down, if we pull this pin down to say -2 volts, we're basically taking 2 volts off that value, and it's an exact add or subtract. So here is the little circuit I've built, and it's very, very simple. Working out how to build this circuit, I did exactly the same as I did for the EC probe. I googled pH probe circuit and clicked on the first link that came along, which was some chap who'd interfaced a pH probe to his Arduino. What did he call himself? Sparky Widgets. sparkyswidgets.com. I found this on, or found most of the information for this. So just before I change the camera to point at the oscilloscope, I'm measuring 2 different points on this circuit. This yellow probe, which is the yellow trace on the oscilloscope, is measuring the output from the first stage of the amplifier. So this is going to be basically the same voltage measurement we're measuring on the probe, but multiplied up so that we can pull a bit of current out so we can measure it with normal test equipment. So that's the yellow trace, and the blue trace is the actual output after I've multiplied it by 10 and shifted the voltage level up. I've got this little potentiometer here that lets me shift the voltage level up and down. So right now we're measuring this probe with this solution in. You can see on this yellow signal coming in, it's saying we're getting about 100 millivolts on average. It's flickering about the place a little way. I suspect this is more the measurement accuracy on this oscilloscope than having a continuous fixed output. I might just hook a multimeter on that, no I won't bother. And then the blue trace is our output from my little circuit, and I've tweaked that until our output value is as close to 0 as I could get it. Right, so now let's see what happens when I take my pH probe out of its little reference solution and I put it into some plain old tap water. Here we go, and there we go. You can see that output voltage there has our input voltage. The scope still can't really tell much difference. It seems to think that's dropped by 50 millivolts, something like that, but our output voltage, you clearly saw it shift up, and we're now reading ½ volt output. So I've just been out and got my bottle of dilute pH down. There we'll stick our reference electrode, in fact we'll stick our pH electrode in our plain old tap water, which has got a pH of about 8 currently, and I'm going to add in a bit of this pH down. Don't know how much I need, that's probably loads. And there we go, you can see the pH come crashing down there. Superb, that looked excellent. Now what I haven't done yet is calibrated how much up or down this line moves on the solution. I need some properly calibrated buffer solutions for that. My pH pen tells us that we've now got a reading of around about 4 down here. 7's in the middle, 8 was up there, so we're running about 8, 7, 6, 5, 4. We're running about 600 millivolt per pH difference currently. Well, that's about it, folks. That's about all I can tell you about pH probes. If I've got anything wrong in that, if anyone knows better than me, please do let me know in the comments, and I'll put some annotations up and correct the stuff I've got wrong, or record a new video or something like that. Oh, while I've got you here, I thought I'll just quickly show you. I made up last week's circuit onto a bit of strip board, so I can just hook that onto a microprocessor. I've got my output pins there, so I can just use little jumper cables, and I'll be doing the same with this circuit over the next week, and start working on actually hooking them up to a microprocessor and getting something to control all my dosing pumps. I was trying to keep this a short one, but I'm actually re-recording this halfway through the editing, and I see it's going to be about 25 minutes long. But it's still early in the day, and I'm really happy about that, because today I'm getting a second greenhouse. My next door neighbour is kindly donating his old greenhouse to me, so I'm going to have an 8 foot by 4 foot little glass greenhouse, and I'll use that as a dirt greenhouse. Anyway, I hope that wasn't too dull for you. Hope some of you found that interesting. Have a great week, folks, and I'll see you next weekend. Oh yeah, they always say, don't forget, rate, comment, subscribe, things like that. I don't really understand why it's important, but it's always nice to look at the YouTube stats and see lots of thumbs up. So cheers, folks. See you next time. Bye.